Okay, so before we proceed with the sample problem to tackle about beam and column design, let us have a quick refresher about the AISC or NSCP design criteria, especially for members subjected to combined loadings, combined compression and bending moment. So for design, AISC H1.1 prescribes the following for compression and bending moment using the LRFD format. So you have to take note, we are gearing towards the use of LRFD because AST tends to be obsolete nowadays. So we will be focusing more on the LRFD, the load and resistance factor design. So according to the code, according to the AISC as well as the NSCP, so have to take note, NSCP natin was just taken from AISC. So everything that you see from AISC, that is just the same thing as what you can see from NSCP. So according to AISC, for an axial ratio, which is equal to PU over VPN, which is greater than or equal to 0.2, for members subjected to combined compression and bending moment, you have to use this interaction equation. P over VPN plus 8 over 9 quantity MUX over V MNX plus MUY over V MNY, which must be less than or equal to 1.0. Okay? So, ang ibig sabihin lang nito, so first equation from the code, kung masyadong malaki, significant, yung axial load or axial compression that is being carried by a member greater than or equal to 0.2, we have to use this interaction equation. Interaction equation is being used to make sure that the corresponding proportion of the stress coming from the axial compression as well as the flexural stress are just properly combined to make sure that their combined ratio will still be below 1.0 or 100%. Okay, so as you can see here, since significant yung axial compression, we tend to minimize the value of the bending moment ratio. That's why may multiply natin siya ng 8 over 9 or 8 over 9 is equal to 89%. So 89% of the bending moment ratio lang yung kinukuha natin. While yung sa axial compression ratio, 100% yung kinukuha natin. Okay. Otherwise, kung hindi naman significant yung axial compression, meaning yung ratio ng PU over VPN is less than 0.2, we have to use this interaction equation. Half ng PU over VPN, 50% lang nito, and then 100% naman yung kabila. And dapat yung sum nila must be less than or equal to 1.0 to make sure that demand capacity ratio will be within the allowable limits specified by the code. Okay? So yung PU dyan ay yung factored axial compressive load. And then yung PN, yung nominal compressive strength considering the member as loaded by axial compression only in accordance with AISC-E3, which is code provision related to compression members. And then yung PhD, yung phi natin, of course, resistance factor yan or yung reduction factor, but may subscription na C, so meaning that is for compression. And yung resistance factor for compression, if you will try to refer sa code, it is just equal to 0.9. Okay. So yung MUX natin dito na ginagamit sa interaction equation will be the factored bending moment about the x-axis, and you have to include the second order effects as well, which is just equal to B1x, MNTx, MNT, or NT, ibig sabihin no translation, plus B2X, MLTX, LT, ibig sabihin yung may lateral translation naman. So ito yung mga amplified bending moment considering second order effects. If moment magnification is used in lieu of computing the elastic second order moments, the term B2X and MLTX applies only for the unbraced frame member, i.e. where sway is possible. Provisions for computing B1 and B2 are in AISC C2.1b. So later on, we will check about that. So you have to take note, yung mga mayu natin dito, ito yung mga factored na PU, yun yung mga factored action compressive load. MUX factored bending moment, but you have to take note, you must always include the subsequent order effects. Okay? Yung mga effects due to being braced or unbraced, so on and so forth. MNX, nominal moment strength for bending about the x-axis as well, kasi nga may x subscript siya. And that can be computed in accordance with AISC-F, which is all about flexural members or yung mga beams. Compression members, ito yung mga columns, usually mga columns. Flexural members, ito yung mga beams usually. Okay. So yung PN mo, kuha natin yan from the topic of columns or compression members. Yung bending moment or yung MN, kukuha natin siya sa topic ng beams or flexural members simply because PN or yung column usually resist axial loads like PN, and yung beams usually resist bending moments like yung MN. Okay. So for the beams or flexural members, yung phi sub B natin is just the resistance factor for flexure or for bending. That's why ang subscript niya ay B. And that is just equal to 0.9 as well. Okay? So yung mga MUY, same lang yan sa MUX, except referred naman siya sa y-axis. So yung definition natin ng MUY, same lang din dito. So banta mo lang lahat ng subscript na X. So refer mo lang lahat sa x-axis. I mean sa y-axis. Okay? Same goes sa M and Y. Same lang din siya sa M and X. Referred lang siya sa y-axis. Okay. So ito yung mga corresponding AISC/NSCP code provisions, starting with the sign of members for combined forces and torsion, which can be found sa chapter H ng AISC. Okay. So kung titignan niyo yung chapter H ng AISC, makikita niyo itong mga topics na to. H1 is for doubly and singly symmetric members subject to flexure and axial force. H2 is for unsymmetric and other members subject to flexure and axial force. H3 is for members under torsion and combined torsion, flexion, shear and or axial force. Okay. Usually ang mahalaga lang naman dito na provision sa chapter H ay yung H1, which is provisions for doubly and singly symmetric members subject to flexure and axial force, such as a member subjected to axial compression and bending. So dito siya pumapasok. Okay? So yung mga formulas na pinakita ko kanina, ito lang din yun. Naka-general form lang siya. Kasi ang code natin, yung AISC natin, naka-general lahat ng formula niya. So that you can easily use them whether you are using ASD or LRFP. Okay, kaya nakaganito yung format niya. Yung pinakita natin na formulas kanina, naka-LRFT na yon using this corresponding values. So, kung kailangan nyo ng naka-ASD, you can just use these corresponding values naman. This is for ASD. Okay. And these are the other code provisions related to members subjected to combined forces. Okay. And then yung chapter F ng AISC, that is the code provisions we usually refer to whenever we design members for flexure or yung mga beams. Usually mga beams yan. So you can see here yung chapter F, marami siyang part dito. F1, general provisions. F2, doubly symmetric compact I-shape members and channel bent about their major axis. Ito mahalaga to. Ito usually mahalaga dyan. F3, doubly symmetric I-shape members with compact webs and non-compact or slender flanges bent about their major axis. Itong medyo okay pa rin naman. Nagagamit pa rin naman to yung F3. F4, other shape or other I-shape members with compact or non-compact webs bent about their major axis. Ito hindi na masyado. F5 for doubly symmetric and singly symmetric I-shape members with slender webs bent about their major axis. Hindi na masyadong nagagamit ito kasi oftentimes nakaka-encounter ng mga members with slender components. F6, I-shape members and channels bent about their minor axis. Hindi rin masyadong nagagamit. F7, square and rectangular HSS and box-shaped members. F8 for round HSS naman. HSS stands for hollow structural steel. F9, T's and double angles loaded in the plane of symmetry. F10, single angles na ginagamit natin yan, yung sa F10. F11, rectangular bars and rounds. F12, asymmetrical shapes. F13, proportions of beams and girders. So ito yung laman ng chapter F for design of members for flexure, pero hindi naman natin madalas ginagamit lahat dyan. Mga provisions. F1, F2, F3 ginagamit. As well as F10. So doon na natin mag-focus sa madalas na ginagamit. Okay. So ito, this is also included in the code. You can refer to this if you just want to know what is the particular member being described dito sa mga corresponding chapter na to. Okay. So as you can see here, for chapter F2, yung mga provisions na yon can be, which is this, yung mga provisions na yan for F2 can be used for sections na may ganitong cross-section, eye tsaka channel. So, kung yung flange nila ay slender, I mean kung compact yung flange nila as well as yung web, dito rin siya pasok sa F2. So, yung mga limit states na check natin dyan ay yung sa yielding tsaka sa lateral torsional backlink. Familiar pa kayo dyan kung naalala nyo pa yung mga yielding and lateral torsional backlink limit states na yan. So commonly yan yung this is your guide. Actually, itong table na to, this is your guide para malaman mo lang aling particular chapters, chapter F, yung kailangan i-refer for a particular section. Okay? So kung pares compact yung flange and web mo, punta ka na lang sa F2. Kapag yung flange mo non-compact or slender, as well as yung web mo compact, punta ka sa F3. Okay, usually ang mga governing dyan, limit state ay yung lateral torsional backlink or yung LTB tsaka yung flange local backlink. Okay. And then kung ganito naman yung cross section mo, compact, non-compact or slender yung flange, tapos yung web compact or non-compact. You can refer to F4 and so on and so forth. So you can just try to refer to this if you just want to know the particular code provision sa chapter F na kailangan mo refer for a particular section. And flange and web slenderness as well as sa limit states. Okay. So, ang mahalaga lang naman dito or yung mga usual natin na ginagamit ay yung F2, F2, F10 yan. Yan na talaga yung pinaka-common. F3 nagagamit din naman. Okay. So, F1, yung general provisions, ito yung laman niya ng code natin. So, nakalagay na dito yung mga strength reduction factor for LRFD as well as yung omega natin for ASD naman. So, itong 0.9, nabanggit ko na ito kanina, this is the strength reduction factor for bending or for beeps. Okay. So, nakalagay din dito yung CB, yung lateral torsional backlink modification factor na ginagamit natin for LTB limit state. So, ito yung formula niya. Kung naaalala niyo pa yung formula niya. And ito yung mga ibig sabihin nung nasa formula niya. So we can just refer to that later on if we will try to use this value. Although commonly yung CB naman is permitted to be conservatively taken as 1 for all cases. Okay. And then F2, ito yung ginagamit natin for checking or for analysis and design of beams, yung common beams natin or flexural members. Okay. So, dito makikita nyo yung mga limit states that you often check for the analysis and design of flexural members. Starting with yielding. So, pag yielding yung limit state na check natin, usually plastic moment yung kinahanap natin, which is just equal to FYZX, where yung ZX is yung plastic section modulus about the x-axis. Okay. We also check the lateral torsional backlink. Meron tayong tatlong cases dyan, which oftentimes depends on the unbraced length ng beam natin or ng flexural member natin. Later on, we will try to use that. And so on and so forth, yung mga other provisions for the analysis and design of steel members or flexural members. Okay, and then lastly, yung mga code provisions for the design of members for compression or simply yung mga columns. So we can find here yung general provisions, E1, E2, slenderness limitations and effective length, E3, compressive strength for flexural buckling of members without slender elements. E4, compressive strength for torsional and torsional buckling of members without slender elements. E5, single angle compression members. E6, built-up members. E7, members with slender elements. So, ang mahalaga lang naman dito, usually yung nagagamit, yung E2, tsaka yung E3, E5, tsaka E7. Ito yung mga laman ng E1, general provisions. Diyan mo makikita yung values ng strength reduction factor for compression or sa columns, 0.9, as I mentioned a while ago, for LRFD. For ASD, yung given natin ay yung omega, yung safety factor na tinatawag, 1.67. And then, yung mga slenderness limitation and effective length that can be found in E2. Okay? So, dito mo makikita, binanggit ni code na preferably, dapat daw yung slenderness ratio for columns preferably should not exceed 200. So, hindi naman siya code requirement, pero recommendation siya ni code. Okay. And then, yung section E3 ng chapter E, dito natin makikita yung mga corresponding provisions for the computations of the axial strength of a column or compression member. Starting with this formula, Pn is equal to FCR times Kg, wherein yung FCR natin can be computed by choosing saan tayo pasok dito na na range sa letter A or sa letter B. So you just have to compute yung slenderness ratio dyan and then compare mo siya dito. So we will try to use all of those provisions later on. Okay. Sa E7 naman, ito yung ginagamit natin. Ito for members to na walang slender elements for compact or non-compact lang or compact sections lang. This is for compact sections. Ito naman for slender sections naman po or yung mga elements na may slender member. So later on, i-review natin paano pa malaman kung compact, non-compact, or slender yung isang section. So you can see here, pag slender yung elements natin, almost same yung formula. Nagkaroon lang ng Q. So you can see here. So yung Q, makakompute natin yan using this other provisions specified sa E7. Okay, so later on, gagamitin natin yan kung magagamit man natin. So yan, yung mga values ng Q, you just have to refer sa code for on how to use those provisions and the corresponding formulas. So additional refresher is yung moment magnifier B1, which is usually used for brace frame. Okay? For members having no joint translation or yung walang non-sway or yung non-sway or brace, we usually use the formula B1 MNT for finding MU. Okay? This is the ultimate moment considering second order effects. Okay? Ito na lang yung formula kapag yung frame natin ay nasa-brace or non-sway. Sabihin wala siyang joint translation na tinatawag. So we have to magnify kasi yung magnitude ng moment acting on a member to consider second order effects. Okay. So yung MNT natin dyan, that is the primary factored moment for the no translation case. Kaya NT siya, ibig sabihin lang nun, no translation. Yan yung mga corresponding moment, factored moment that you can have for a member na walang sway or non-sway or naka-brace siya. Okay. Wherein yung B1 natin dyan, yung moment magnification factor na tinatawag, is just equal to Cm over 1 minus alpha times Pu over Pe1, which must always be greater than or equal to 1. Obviously, dapat greater than or equal to 1 yan kasi magnifier nga siya eh. So, ang purpose niya is to magnify the value. Pag less than 1 yung value niya, ibig sabihin, hindi na niya minamagnify value. Okay? So, yung formula niya, makikita mo rin sa AISC C2-2. Okay. So, yung alpha dyan is just equal to 1 for LRFD or 1.6 kung ASD naman yung gagamitin. So, focus naman tayo sa LRFD. So, it's as good as wala na tong alpha dito kasi nga, pag LRFD, 1 lang naman yung value niya. Yung value ng CM can be found from the code, especially here. Yung CM is a coefficient assuming no lateral translation of the frame whose value shall be taken as follows. At yung dalawang value ng CM, CM can be equal to 0.6 minus 0.4 quantity M1 over M2 for beam columns not subject to transverse loading. Okay, yung mga column or yung mga members natin na walang transverse loading, we can just use yung CM is equal to this. For beam column subjected to transverse loading, or yung may mga loads along the body of the member, you can just compute CM using either by analysis or you can just conservatively use 1 for all cases. Okay. So, if pasok ka dito sa letter or sa Roman numeral 2, yung member natin ay may transverse loading, you can use the values of CM using this derived formulas using analysis, which is just equal to 1 plus psi alpha or 1 plus psi PU minus PU over PA1, where yung PU factor reduction compression load, PA1 is the Euler load using KL over R for the axis of bending with K is less than or equal to 1.0 for base frame, and then yung mismong value ng PA1 is pi squared EAG over KL over R quantity squared or equal din sa pi squared EI over K1L times quantity squared, which can be found sa AISC C2-5. So pares lang yung formula na yan. Ang nangyari lang, yung AG natin tsaka R pinagsama para makabuo ng moment of inertia. Since we know that I, moment of inertia is just equal to AGR squared. Okay. And then yung psi can be found sa table C2.1. Okay. And then ito, additional code provisions related to analysis and design of members. yung mga requirement for second order effects. So ito na nga, ito na rin yung pinakita ko kanina, yung mga formulas. M is equal to B1 MMT plus B2 MMT. So dito na rin siya makikita. Formula for B1 is equal to CM minus over 1 minus alpha. So ito rin yung pinakita ko kanina. And so on and so forth. And yung formula for P1 nakalagay na rin. And then additional code requirements for second order effects as well as a first order analysis nakalagay na rin dito sa code. So, lagay na lang natin for your information.